Hi, my name is Brian Caffo, and this is the lecture on least squares estimation of regression lines in the Regression Coursera course as part of our data science track. My name is Brian Caffo, and this course is co-taught with Jeff Leek and Roger Peng. We are all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so hopefully you've watched the previous lectures and where we've kind of gone over some of the basics and then also gone over notation. Let's consider the parent and child data sets again from Galton. And here it is. Remember, the size of the circle represents the number of points at that particular XY combination. And now we would like to fit a regression line through that data, so a line that in some sense is the best line through the data. And that's what we're going to talk about today, and we're going to talk about doing it with least squares. So let's let yi be the ith child height and xi be the ith parent's height, which is the average with the correction that we talked about previously. And we'd like to use parent's height to predict children's height. And so we're going to try and do it with a line. Child's height is beta naught plus parent's height times beta 1. And to find that line, why don't we use so-called least squares? So what we'd like to do is, if this was the regression line, remember that the regression, a line only takes two parameters to describe, a slope and an intercept. And so if we had that regression line, if we were to plug in, say, a child height, xi, and multiply it times the slope, beta 1, and add the intercept to it, beta naught, then we would get the predicted, if we were to take a parent's height, xi, and multiply it times the slope, beta 1, and add the intercept to it, beta naught, then that would give us a predicted child's height based on the regression line. Yi, in contrast, would be the actual child's height, not based on the regression line, the one that was actually recorded. So the difference between these two is the difference between what the model would predict for that child and what actually was observed for that child. And so why don't we, as a criteria for the best line, minimize the sum of those squared distances? In a pictorial sense, that is, if we have a bunch of data points like this, right? That's trying to fit the best line through the data that minimizes, this is that distance. This would be yi, and this point right here would be beta naught plus beta 1 xi. And we want to minimize the sum of these squared vertical distances. And we square them, of course, so that we have always positive things, so that being a certain distance below the line is equivalent to being a certain distance above the line, the same distance above the line. So how do we do it? Well, I'm going to, again, so if you're not interested in the mathematics, the homework questions and the quiz questions won't focus on the mathematics. So this is, again, right now, only if you're interested in the details. If you're not, you can skip ahead a couple of slides. But I'm going to go through all the details again without requiring calculus or linear algebra. So let me let mu be beta naught, mu I be beta naught plus beta 1 xi, just to reduce some notation. Then our estimate would be mu I hat if we found a specific value of beta naught hat, and a specific value of beta 1 hat, then our fitted mean would be mu I hat for that pair. Okay, so we want to minimize yi minus mu I, where I've just now replaced, in the previous equation, replaced the beta naught plus beta 1 xi now with mu I. We want to minimize the sum of yi minus mu I squared. Well, why don't we add and subtract like we did with the mean when we didn't have a regression line, we just wanted to do the mean. Why don't we add and subtract a mu I hat and then expand that square, and we get this set of equations right here. And if this term right here is 0, in other words, if this term right here is 0, then then we wind up with this equation right here. But notice this is the sum of a bunch of squared things. Squared things have to be positive, so if we discard this, we only get bigger. So the end result is we'll find the best mu I. If that condition is met, then the mu I hat that we come up with will be the best one. And we're only going to search among mu i's that satisfy this criteria, that they are beta naught plus beta 1 xi. We would get a different mu I if we allowed the mu I to have a different criteria. Say if we added another one, beta 1 xi plus beta 2 zi or something like that, we would get maybe a better fit. But right now we're only going to do it with the single line. Okay, and so the key is if we can make that condition, and the reason I do it is because we'll just use that condition in all the different ways we develop regression later on. We just note that that condition has to happen, and then if we can find something that satisfies that condition, then we will have found the least squares estimates.